Hello, my name is Dr. Liam Bullock. I'm the Head of Science for Carbon Neutral Initiative, and with this presentation, I will cover what a CO2 removing green roof is, why we need them, how it works, and what we aim to achieve. I'll start by explaining the global climate challenge, essentially why we are doing this in the big picture. This IPCC graph illustrates a pathway towards achieving net negative greenhouse gas emissions by 2100, which is our ultimate societal goal to avoid irreversible climate change. The simple explanation is that to meet our climate targets, we need to reduce our greenhouse gas emissions dramatically, but we also need to actively remove CO2 directly from the atmosphere, and we can do this by either nature-based solutions or human-made approaches. Our nature-based solution aims to capitalize on natural methods of CO2 removal. Specifically, some rocks and minerals react with CO2 to remove it naturally, and importantly, remove it permanently, which is something that's not guaranteed with storing CO2 underground or in any types of vegetation, such as planting or growing trees. Rocks and minerals actually already remove around half a gigaton up to 1 gigaton of CO2 per year without any human intervention. But there are still two issues that we face. One is that this is only a minor amount removed compared to how much we emit every year. And two, the process is a slow one. It takes thousands of years or longer for natural removal to occur without any intervention. Our aim is to speed up the process so that rather than it taking thousands of years to achieve high amounts of carbon removal, we are achieving this in human relevant timescales, such as decades or less. Nature-based approaches like enhanced weathering are a scalable way to achieve this aim, as the land already exists and it does not impose any additional infrastructure or footprint compared to human-based approaches. And there is also no risk of leakage of the CO2 once it's been removed. Nature-based approaches can also bring co-benefits to the soils that they're deployed in by adding nutrients, counterbalancing acidity, and improving soil structure. So here is how enhanced weathering works. Enhanced rock weathering aims to replicate a natural part of the Earth's carbon cycle. Natural weathering involves rainwater reacting with rocks, which can contain magnesium and calcium, to release these elements, which can then react with CO2 in the rainwater and in the atmosphere to produce a bicarbonate solution, otherwise known as alkalinity. Essentially, the CO2 is transformed into alkalinity, removing it from the atmosphere and storing it in a bicarbonate solution, which is then transported to the oceans via rivers and groundwater, where it can reside for thousands of years. Eventually, some of that alkalinity may precipitate out to form carbonate minerals, which is also a permanent storage method. This natural weathering process takes thousands of years to occur. Enhanced weathering aims to speed up that reaction. The best way to speed up weathering or dissolution of a solid substance is to take it and crush it. It works for sugar cubes, for vitamin tablets, and it also works for rocks and minerals too. So we crush the rock and we add it to the soils, where the soil processes, the biological processes, the higher concentrations of CO2 and the acidic conditions all act to speed up the release of calcium and magnesium from the minerals, and then for the conversion to bicarbonate alkalinity to occur within human relevant timescales. And the rest of the process is the same as the natural weathering process, where products are transported to the ocean for final storage and some precipitation. So for enhanced weathering, we add what we call a feedstock, which is essentially a rock or a mineral, to the soil, and then we let the rainwater do the job to react with that rock and in the soil with the CO2. So rainwater falls on the soils and the rainwater flows downwards so that the reactions can occur in the mixed soil and feedstock. And the CO2 is removed as bicarbonate solution, which is transported downwards through the soil profile. The products are transported via groundwater flow, via rivers and via streams or drainage systems, ultimately ending up in the ocean for its final and permanent storage, where it resides as alkalinity for tens of thousands of years. In terms of feedstock selection, part of our job with Carbon Neutral Initiative is to select the most appropriate feedstock, be that a rock, a mineral, or any kind of solid material that can react with CO2. Now, the ideal feedstock will contain calcium or magnesium or both to react with CO2 to form our stable bicarbonates. We also want to use fine-grained materials, such as finer than sand particles, right down to powder-like sizes for faster reactions. The most commonly used feedstocks include rocks that originate from magmas or volcanoes, such as basalts, an olivine, or an olivine-rich rock called dunite. We've chosen to target a calcium-rich silicate mineral called wollastonite. We believe wollastonite is an ideal choice for a CO2 removing feedstock, as it readily and rapidly reacts with CO2 to form alkalinity or carbonate minerals, much faster than rocks such as basalt, and contains very little in terms of potentially harmful trace elements such as nickel or chromium, which can occur in quite high amounts in rocks such as dunite or minerals such as olivine. So it is essentially a safe, fast-reacting material for CO2 removal. Additionally, wollastonite can help improve soil health by increasing pH and reducing acidification, which can increase plant and crop health. So the ideal feedstocks will be fine-grained and will be rich in calcium and magnesium silicates. So as I say, other than wollastonite, other options are olivine, which is rich in magnesium, basalt, or a similar rock known as gabbro, which contain calcium and magnesium, and also any industrial byproducts which are derived from these kinds of host rocks. So glassy slags and mine tailings from rocks which we call mafic or ultramafic rocks, essentially those which contain high amounts of magnesium and calcium. Our product is the CO2 removing green roof for use on urban rooftops, on surfaces and in infrastructure, whereby adding our wollastonite feedstock to the green roof substrate helps to make buildings more sustainable and contribute to climate transition goals, removing 10 kilograms of CO2 per square metre. Beyond CO2 removal, green rooftops provide thermal and sound insulation, increase water retention, increase urban biodiversity by providing habitats for birds and bees, for instance, and extend roof life, meaning less maintenance is required. These installations also provide a visual demonstration of climate action, which is both aesthetically pleasing, but may also act as an example for others to adopt. And the inherent benefits of the green roof can be advantageous for CO2 removal, as things like water retention and plant growth can help speed up reactions in the substrate. As the benefits and co-benefits of our CO2 removing green roof, the addition of wollastonite can ensure long-term CO2 removal, which can help to achieve local, national and international climate goals, but can also aid in plant resilience and soil structure, result in deacidification of soils and ultimately the ocean, increase water retention, provide insulation for both heat and sound, extend roof life, and reduce maintenance. It can also increase urban biodiversity and provide a visual, pleasing demonstration of climate action in public and commercial areas. We know that the climate challenge is an imminent task, and we need to work on every possible scale to achieve global targets. Enhanced weathering and green roofs is a scalable approach, it's ready to deploy, and it could remove gigatons of CO2 on a yearly basis. And adding this to green roofs can provide many benefits beyond CO2 removal. If you have any questions, please do not hesitate to reach out to us at Carbon Neutral Initiative. Thank you.